Alright, so in the previous video we looked at differentiating from first principles, but we don't really want to do that every single time we want to differentiate something, right? Because it takes too long. So we need to find a rule which allows us to differentiate much quicker. So for very basic terms where we have x raised to a certain power of n, if we were to differentiate this, then all we need to do is bring the n down and bring it, multiply to the x, and then to the power we just minus 1 to the power. So we get nx and minus 1. For example, if you have y is x squared, if I were to differentiate this, I bring the power down, so it's 2 times x minus 1 to this power is power of 1. Same thing for x cubed, bring the power down first, so it's going to be 3x minus 1 to the power is going to be 2. This is the same case, so if I said like y is 2x to the power of 4, for example, even though we have a 2 in front, we leave that 2 separately, and then you just imagine differentiating x to the power of 4, so 4x, 3, so it's 8x cubed. That's why in this case, indices are very important to know. So if I gave you something like y is root x and I want you to differentiate this, in this type of stuff, we always want to change it to indices form. So we say x to the power of a half, and then we differentiate this, so we get half x to the power of minus 1 to this is negative a half, like that. So you need to be very, very comfortable with indices. Even stuff like, let's say y is equal to 1 over 2x plus cube root x plus 4. So in this case, we have 3 different terms, right? But it's the same method. We deal with each one separately. So first thing, I'm going to change it all into indices form. So this is 1 over 2 x to the power of minus 1 plus x to the power of 1 over 3 plus 4. Now I can differentiate this. So this is minus a half times x. Minusing 1 to this is minus 2, right? Plus 1 over 3 x minusing 1 to a third is minus 2 over 3. And for this 4 here, there's no x terms, right? So whenever we differentiate as just a single number, any number, it just disappears, and so we're just left with this term here. So this is a very basic way of differentiating x raised to a certain power, and with this we can solve a bit more tricky questions such as these ones here. So let's just try some of these here. So let's try a first. So y is 2 root x. So as I said, all you need to do first is change it into indices form first. So this is going to be 2x to the power of a half, which I can now differentiate. So leaving the 2 there, times by a half, x minus 1 to the power is negative a half. So this is x to the power of negative a half, like this. If we were to try maybe 1 over y is 1 over c, 1 over 3 x cubed, changing to indices form first, that would be 1 over 3 x to the power of minus 3. dy by dx is 1 over 3 times the power, so negative 3x minusing 1 to that is minus 4. So negative x to the power of minus 4. We can even deal with stuff like d, where we have y is 1 over 3x cubed times x minus 2. As you can see, we have two functions multiplied to each other. So what we need to do now is to expand the brackets first before differentiating. So this would be 1 over 3x to the power of 4 minus 2 over 3x cubed. And now I can differentiate each one separately. So this would be 4 over 3x cubed minus 2x squared, like this. This works with dividing as well, so let's try I. So we have y is equal to 2x cubed plus 3x over root x, like this. First things first, I want to change it to indices form. So this is 2x cubed over x to the half plus 3x over x to the half, which will give me 2x. Using the indices rule, when we divide, we just minus the indices. So we have 3 minus a half, which is 5 over 2, plus 3x to the half. Now I can differentiate it, so dy by dx is equal to 5x to the power of 3 over 2 plus 3 over 2x to the power of negative a half. So as long as you change it into a certain indices form, then the rule still stands. You bring the power down, and then you minus 1 to that power to differentiate.